Hey everyone, it's Mr. Anderson. Today we are going to start a new unit in our CPM ebook. And today we're starting the first unit or the first lesson in Chapter 6. And Chapter 6 is all about modeling with two variable data or bivariate data. And this is big. It could lead us on into some big, broad thinking in terms of how data looks, what kind of a picture data paints, as well as what kind of modeling we're able to do with that data. Normally, we would be doing some of these things very much together and in class, and today I'm going to have to ask you to do some imagining. And if you're not sure what I'm talking about, the only thing you're going to need to do, if you can't imagine what I'm talking about, is grab something like a toilet paper roll or a paper towel roll, and I will talk with you about what we might be doing in class if we were in person. I've got a couple workarounds for us because we can't be in person right now. Okay. There is a problem that we're going to use to frame some of the modeling that we're going to be doing, and it is laid out here in 6-1. It says the championship is on the line between Tinker Toy Tech and City College. Robbie plans to attend Tinker Toy Tech next fall and desperately wants to see the game, which has been sold out for weeks. Surveying the exterior of the stadium, Robbie has discovered a small drainage pipe that has a direct view of the field. The stadium is being prepared for the big game, and a maintenance van is currently blocking the view from the pipe, but the van will be moved prior to the game. Okay, so here's kind of the situation. We've got our field, and there is a drainage pipe on the south end, and Robbie could stand outside of the field because he can't get a ticket in. It is sold out. He can look through the drainage pipe and he can see the game going on, okay? So the south end of the field is 50 yards from the end of the pipe, and the field runs north to south. The total length of the playing field, including the end zone, is 20 yards. The pipe will be at the center of the south end of the field, and the width of the field is 53.3 yards or 160 feet. Investigate how much of the field Robbie will be able to see when he looks through the pipe at game time. Now, I'll share with you as somebody who does stats and deals with data, a necessary part of these things is going to be collecting data. And again, we can't have you doing these things in person, but like I said, if you grabbed one of these, this would be kind of how we're going to look at doing something like this. Imagine putting this up to one eye, closing one eye, and then just looking in the same direction you're looking at, maybe removing it once or twice. Notice what happens, right? We get a limited field of view, okay? I'm actually going to even make this bigger, right, so you can see me. We get a limited field of view, right? You can still see all of me, but as I'm looking, I can now only see my computer screen, whereas if I do this, I can see like the entire room. And that kind of changes, right? I've got a short tube right here. This is a toilet paper roll. Right here, maybe you've seen something like this. This is a foam roller, okay? And even if I put this thing up, right, it's a longer tube, it's got a bigger hole, I get slightly more of that field of view looking through this than I do looking through this, okay, but it's not significantly more, right? So there's a limitation. And Robbie, as he's looking through the drainage pipe, is going to experience a similar experience, right? There's going to be a similar effect, right? So we've got to create a model for the data collection. And like I said, if you were in class, if you were showing up and in person, I'd have toilet paper rolls for you or paper towel rolls for you, and we'd be doing this collection. Okay? But I can't do that right now, so I generated the data, and the data is going to be on my notes on my iPad. My iPad code is 1323 in case you were wondering. And here is our diagram of the Tinker Toy Tech football field, and the end of the pipe, as you can see, is 50 yards at my 100-yard field, and there is 10 yards for each end zone. I collected some data for you, okay? Now, normally we'd have you set up, you'd be 144 inches from the wall, which is about 12 feet, and you would be seeing how much of the width of the field that you could see. I'd have a little marker on the wall, and you'd have to do some measuring in teams. Then I would have you step closer, right? Move a foot closer, and then move another foot closer, and so on and so forth. We'd be collecting the the data the entire way. And I want you to see what's happening here. The closer you get to the wall, or the closer you get to the field, the less you can see. And that actually is true. And if you don't believe me, grab this, right? And if I back up, I can see more around my computer. If I come closer, the screen, the field of view narrows, right? And that's kind of what we're seeing, and that's going to be an important relationship. And in part B, in this particular problem, we're going to take that data and we're going to make a scatter plot of the data. And I did this already, but I'll remind you real quick of what this is going to look like, the process, because the process is the important part. If you ever had to do this, I've got a Desmos tab just open, and I can go ahead and I can simply click and I can add a table, and I can type in the data as I see it. The first point was 144. I'll tab over 20.7, and I can just keep going. 132 and 19.6. I can keep going. 120 and 17.3. And now, ladies and gents, I can just zoom and change. I know I've got my bivariate real world data is going to create a scatter plot, which to me is a quadrant 1 graph. And now I can see that graphed here. I can open up my settings and I can adjust the windows to do that. And that's how I arrived at this graph. And it says describe the relationship between the distance from the field and the field of view, or distance from the wall, I'm sorry, and width of field view. And what we see here is we've got a strong positive relationship. Now, how do we know that, or where have we seen that before? Well, way back here in our CPM ebook, you can see that we've got a math notes all the way back from chapter 4. And I'm going to click on that, and it's got a couple of hints for me here on describing an association. Okay, we've got a negative association, one that trends down from left to right. We've got a positive association, one that trends upward from left to right. And ladies and gents, these are both linear models. Here's a non-linear model. So I said ours is going to be positive, ours is going to be linear, and I actually said because all of my data I think is really going to fit pretty tight to a line of fit, and I'll remind you of what that is and how to make that in just a moment. All of our data is going to fit pretty tight to that. We're going to have a strong linear model, okay, or a strong positive linear model. And that's what I have right here, a strong positive linear relationship. Next part says draw a line of best fit. Now, this I think is the pretty gosh darn easy part for a lot of students, and you might remember this from a 9th grade or 8th grade science class, okay? And a line of fit really should try to go with the trend of your data and split your data in half-ish, right? We should have the same number above and below our line. And that's going to be a pretty good thing. If we ever needed to do this with exactness, we would use a computer for it. But the point is to come up with something for the purposes of prediction. Now check this out. If I drew a line of fit like this, one could argue that I split my data in half. The problem is that doesn't go with the trend of my data. So don't hesitate to look back here and look at how my lines of fit are moving. Okay, they're moving in line with my data, and this should be no exception here. I will advise you because, oops, I had the eraser, because this goes all the way through there, I have the possibility to go all the way through to the x-axis. I could do an extension all the way through. I'm sorry, I said x-axis, that's the y-axis. An extension all the way through to the y-axis, because I'm going to care about that in just a moment. Then it says for me in part C to write the equation of that line of best fit. And this actually isn't too bad. I've just got to remember I've got a y-intercept, and I'm going to suggest that y-intercept is, I don't know, about 1.5. So I'm going to write this thing in y equals mx plus b form, mx plus b, and my y-intercept I just said is about 1.5, and it's okay to estimate here. And then I've got to figure out what that slope is. And for this, I'm going to use the slope triangle. And when I use the slope triangle, I'm going to find some pretty gosh darn nice points. And I'll use like a color like orange to help me out with this. This is pretty good right here. I'm going to say that it crosses right about there, and I'm going to say it crosses right about there, and I'm going to go up this many, and I'm going to go over that many. Now, how many did I go up, and how many did I go over? Well, I went up from 14 all the way to 18, so I went up 4. And then I went over from 90 to 120, so that to me is 30. So I went up 4 and over 30. Now, a little bit of math here might help me, and I've got real quick a what's this thing called, a cell phone there. I'm trying to find my calculator app. I take 4, I divide it by 30, and that tells me my slope is 0.133. So y equals 0.133x plus 1.5. All right, and we've got a line of best fit that looks something like that. Now it says here, hey, what do the slope and the y-intercept represent? And the slope and the y-intercept are actually very important, okay? If we've got a y-intercept, that represents the value of y when x is 0, okay? So that would be like, I'm looking through this like tube, and it's when the tube is 0 inches from the wall, okay? 0 inches from the wall. Well, what would I be able to see there? I'd be able to see only the edge of the tube. That means the diameter of my tube is about 1.5 inches. Okay? That's important, okay? But then what does the slope mean? Because the slope's a rate, it's a little tougher. The slope is going to represent how much gain we have for every movement we have to and from the wall. And the representation here, you can always put this over 1, 0.133 over 1. The, how to put it, 0.13 inches of field view is gained for every inch I move away from the wall, for every inch of gain I have moving away from the wall. And that's the way that we can represent that slope. And those are bigger ideas. We're going to keep developing those, but we might as well start doing that right now and today. Okay, we've got then one last question, and this is the point of doing this, and I want to make sure I have enough time for this. The point of doing any sort of line of fit or regression model, I know you haven't heard me say regression yet today, but the purpose of my line of fit is for predictions, and that's what 6-2 is for. So I want to get to this. It says, predict how far in yards Robbie's field of view will be at the south end of the field. How wide will it be at the north end? Well, we're going to use our model to make this prediction. And my model is 0.133, and I did round that, plus 1.5. And it does say predict this in yards. Now, he's got a field of view, and I've got to back up here. He is, if you recall here, he's 50 yards from the edge there. So I'm going to go like this, and I'm going to just quickly, I'm going to say, all right, well, let's see. I'm going to take this, and because mine deals with inches, so I'm going to take 50 because he's 50 yards. I'm going to multiply because there's 3 feet in every single yard. All right, so that's 150 feet. And then there's 12 inches in every single foot. So that to me says that he is 1,800 inches from the edge of the field there. So what I'm going to do is I'm going to plug in 1,800 for my x value here. And this is some plain Jane linear algebra. Take that value, multiply by 0.133 plus 1.5, and it tells me that my answer is about 240.9 inches. And when I divide that by 12, I get 20.075. When I divide by 3 to convert to yards, I get about 6.69 yards. Okay? I'm not going to make the prediction from the north end of the field just because of time today. But ladies and gents, there is a tiny bit of review preview here, 6-4 to 6-7, that's going to really give you an idea of what kind of questions you might have. Thanks for watching.